All right, welcome. Today, we're going to dive into a science that's kind of hidden, but it literally powers our entire modern world. It might not sound glamorous, but trust me, it's absolutely essential. We're talking about the science of separation. I mean, have you ever really thought about it? How do we take a complex jumble of liquids and turn it into something pure and useful? The secret isn't some kind of magical filter. Nope. It's all about a deep understanding of how liquids and their vapors interact. And getting this right is a huge deal, a really huge deal. In a typical chemical plant, these separation processes can eat up a whopping 70% of the total cost. It's one of the biggest, most expensive challenges in all of industry. So yeah, understanding it is key. So here's our roadmap for today. First, we'll tackle that 70% problem and why separation is such a beast. Then we'll get into the cool science of phase maps and this key property called volatility. From there, we'll see how distillation puts it all into practice. And finally, we'll zoom out and see how this one idea literally builds the world around us.
Okay, let's start with that 70% problem. Almost every single commercial process you can imagine, from brewing your morning coffee to refining the fuel that gets a jet in the air, involves separating stuff. And separation isn't just one single thing, right? There are tons of ways to do it. That coffee you made this morning, that's a process called leaching. Cleaning up factory emissions, that often uses absorption. But getting valuable chemicals like methanol out of water, that requires distillation. And that's going to be our main focus today. Each one of these techniques is just a clever way of exploiting a physical property to get the job done. So how on earth do engineers know which method to pick? Well, they start with a map. Seriously, it's a special kind of map that shows them exactly how a substance is going to behave under different conditions. This is where something called a phase diagram becomes absolutely essential. The whole goal here is to reach a state of, balance. It's called phase equilibrium. Just think about leaving a glass of water out on the counter. Water molecules are going to evaporate into the air, right? They'll keep doing that until the air just can't hold any more water vapor. That's equilibrium. The system is stable, and engineers use that predictable point of balance to design all their separation gear. So this is it, the phase diagram. It's literally a map. It's a visual cheat sheet that tells you if a substance, like water, is going to be a solid, a liquid, or a gas at any combination of pressure and temperature. For an engineer, a map like this is just as crucial as a blueprint is for an architect. And just like any good map, this one has some key landmarks you gotta know. There's the triple point, a wild spot where a substance can be a solid, liquid, and gas all at the same time, and the critical point where things get so hot and pressurized that liquid and gas become indistinguishable. But for us, the most important landmark is that vapor-liquid curve. That's the line where all the boiling and condensation action happens.
Okay, so we've got our map. Now we need to understand the force that actually drives the separation. And that force is a property called volatility. You could call it the secret sauce that makes this all possible. So what exactly is volatility? Well, the absolute best way to think about it is as a substance's eagerness to escape. It's how badly it wants to break free from the liquid phase and become a vapor. Some liquids are super eager to escape, and others, they're pretty happy just staying put. And that difference, that's what we're going to exploit. Let's make this super simple. Think about alcohol versus water. When you put on hand sanitizer and poof, it's just gone? That's because alcohol has a really high urge to escape. It's very volatile. Water, on the other hand, is way less volatile. A puddle of water sticks around for a lot longer. In engineering speak, this just means alcohol has a higher vapor pressure. And this right here brings us to the single most important rule in all of separation science. When you heat up a mixture of liquids, the vapor that comes off will always be more concentrated or richer in the more volatile stuff. It's a simple, natural law, and it's the key to everything. All right, so we have this core principle. Now let's see how it gets put to work on an industrial scale with a process called distillation. This is how we take that simple idea of volatility and use it to purify massive, massive amounts of liquids. Okay, so quick pop quiz for you. Let's say you heat up a liquid mixture. It's got component A, which is more volatile, and component B, which is less volatile. What happens? Well, the answer is C. They're both going to vaporize to some extent, but, and this is the key part, because A has that higher eagerness to escape, the vapor that forms will have a lot more A in it than the original liquid did. And this is where the magic of distillation really happens. It's basically just a clever cycle, a rinse and repeat process. First, you heat the mixture. The vapor that comes off is richer in the good stuff. Then you capture that vapor and cool it back down into a liquid. And guess what? This new liquid is purer than what you started with. So you do it again and again. And with every single cycle, you get a higher and higher level of purity. Now, to do this with incredible precision, engineers use another special tool called a TZPY diagram. Now, don't worry, we are not getting into the math. But basically, this chart is like a playbook for a specific mixture. It tells an engineer the exact temperature to get the first vapor bubble. That's called the bubble point. It maps out the entire process, making these huge industrial-scale separations possible. Okay, we've been deep in the science, so let's pull back and see just how massive the impact of this one fundamental idea really is on all of us. I mean, just take a look at this. Making chemicals and fuels is almost completely dependent on getting separation right. But it doesn't stop there. Life-saving medicines, and even the food and drinks we have every day, all of them rely heavily on these processes for purity, for safety, and for quality. Seriously, just think about it for a second. The gasoline in your car, that comes from distilling crude oil. The pure oxygen a patient breathes in a hospital, separated from the air. The incredible purity needed for our medicines, the clean water we drink, even the distinct character in spirits like whiskey and vodka. It's all a product of these fundamental principles of separation. It is everywhere. So, what's the big takeaway here? The science of separation is this quiet giant, shaping our world from the fuel in our tanks to the water in our glass. And as we look to the future, facing huge challenges like resource scarcity and climate change, it leaves us with a really important question. How can we harness this incredibly powerful science to better recycle materials, capture carbon, and build a truly sustainable world? The principles are the same, but the applications, well, the applications could change everything.